Okay, where were we? Let's get back to it. We just did these two very exciting examples using the definition of the definite integral, infinitely many rectangles, really fun. To wrap up this section, these are like the big keystone sort of problems, right? This idea here is going to lead us into the fundamental theorem of calculus in 5.3. But before we wrap up, let's mention maybe an example like this one. Evaluate this definite integral using formulas from geometry. They might present us with some definite integrals that would be extremely difficult or even near impossible for us to do using the definition of the definite integral. Something like a function with the square root, right? We don't have summation formulas for that sort of thing. But we still could figure out the definite integral if we thought of it as a shape and we used area formulas that we know from geometry. So let's take a look at this one, the definite integral from 0 to 5 square root 25 minus x squared dx. Evaluate using formulas from geometry. Integral 0 to 5 square root 25 minus x squared. Okay, dx. From geometry. So we're not going to attempt our limit as n goes to infinity, summation, all that. No way. We're going to think, what does the graph of this look like? Think of it as y equals square root 25 minus x squared. Well, as it is, that's probably doesn't look very familiar, but maybe we could rewrite this in such a way as to, maybe that will be more familiar to us. What if we were, say, to square both sides, right? I mean, what else can we do, right? We can get rid of the square root. Y squared equals 25 minus x squared. Does that look more familiar? Maybe not. What if we were to add this x squared over here? Does that look familiar? Maybe. That is the graph of a circle with a radius of 5. Aha. So it turns out we can use our knowledge of the area of a circle to figure out what this definite integral would be. Now, here's the thing. Well, x squared plus y squared equals 25 is the entire circle. If we move back and isolate the y, if you think of moving backwards, here we would have square rooted both sides, which should have given a plus or minus. But we don't have a plus or minus there. We just have the plus. What's up with that? Y equals the positive square root 25 minus x squared is the top half of the circle. It's the half where y is positive. Y equals negative square root 25 minus x squared is the bottom half of the circle, where y is negative. So when we're given this, right, we're only given the upper half, the positive y values. So we don't want the area of the entire circle. We just want part of it. And you know what? I'm looking even closer. It actually says from 0 to 5. So we don't even want the entire upper half. We only want the portion in the upper half going from 0 to positive 5 right here. So a quarter of the circle. So to get this definite integral, it's equal to that area. Well, okay, that's 1/4 area of a circle. The entire thing is pi r squared. We want a quarter, our radius is 5, a quarter times pi 5 squared. This would equal 25 pi over 4. We got it. So that seems maybe like these sort of questions, they'll kind of sneak in. The idea is really to just lay that foundation of what this represents. So we're telling you a function, right? We're telling you where to start and stop. You know, typically these areas are not going to be possible using formulas from geometry. We're not just going to have triangles or circles, right? They're going to be these funky curved quadratic or cubic, or, you know, eventually we'll get stuff with, you know, square roots and sine and cosine and e and all that. But for now, you know, we just really want to sort of cement that idea that to find this stuff, we're finding areas. Okay. Very good, very good. Let's go back to the lecture. One more piece to this. Properties of integrals. We want to end this section just by laying out a few things that are true for definite integrals. These will kind of remind you of some of the simpler rules for derivatives. And there won't be much explanation given for these properties, but hopefully, you know, they seem intuitive enough, and maybe we can draw some pictures of a couple of them. Okay, so the first property, if we've got a constant being multiplied by a function that we're taking the integral of, so we'll call it c f of x. For any constant c, just like in a derivative, we can move that constant out to the front and think of it just carrying along when we do the integral. So c times f of x, we can think of it as c times the definite integral. Okay, makes sense. Property number 2, what if we're adding or subtracting two functions? So we've got the definite integral from a to b, f of x plus or minus g of x dx. Well, it would be perfectly fine to perform the integral for each of those functions separately. Again, very much like a derivative. Actually, really where this comes from is that's what you would do with a limit. So if that's what you would do with a limit, then you can do it for an integral as well. Okay, how about this is kind of a funky one. Notice that the upper limit on that integral is also an a. So this is the integral from a to a, f of x dx. That would equal 0. Why is that? Well, your starting and ending values are at the same place. So there's no width at all to your area. It's just like a line. And yeah, I mean, that area would be 0. Okay. This is kind of an interesting one. If you reverse the lower limit and the upper limit, the a and the b, then it becomes negative. All right, it's kind of along the lines of when you go beneath the x-axis, the area becomes negative. Well, if you move in reverse, right? So you could almost like think of this one, a to b, as moving from left to right. If you switch them, and now you're starting at b and ending at a, maybe you're thinking about like, well, that's moving from right to left, thinking of the area that way, and the area would become negative in that case. And finally, our last property, if let's say you're taking the integral from a to c, f of x dx. What if there's a number b, right? Maybe it's between a and c, although it actually wouldn't have to be. But that's probably the easiest thing to think, that b is somewhere between a and c. Well, you could take the integral from a to b, and then you could add the integral from b to c, and those together would make the integral from a to c. Maybe really fast, let's draw these last couple of them. We can sketch these. So property 3 was a to a f of x dx equals 0. Why is that? Well, if you thought of a function f of x, but your starting and ending point was at the same location, a, well, yeah, the area is 0. The next one, a to b f of x dx is equal to negative integral from b to a f of x dx. By the way, whenever you read these, always read the number on bottom first. From a to b, this you would read from b to a. Why would it be the negative? So if you were going, say, from a to b, this direction, right? That's how we would normally think of it. That would be positive. If you were to reverse it, and go from B back to A, moving from right to left, that area, when you do the math, would come out as negative. And then finally, from A to C, f of x dx, we said is a to b f of x dx plus integral from b to c f of x dx. The simplest drawing, maybe something like this. Here's A, here's C. And so all of that would be the same as going, say, from A to B, and then from B to C. Although the truth is, B could be outside. All right, let's maybe, here's A and C and B this way. This would still work. That would still be true because A to B would go all the way here, but then B to C would work backwards and would count as negative area and would erase this, and the net would just be from A to C. So that's kind of, I don't know if we'd really ever do that, but it would be true. Okay, so you'll see some questions in the homework based on these properties. We won't do any examples. You can just dive right into those. That's it for 5.2 and the definition of the definite integral.